lecture we will be it is a fifth lecture on Laplace transform and final lecture. It is based on the application of Laplace transform to solve convolution type Volterra integral equations. So consider a equation like this, and the integral should be of form like if we want to solve any integral using Laplace and transform, the integral should be of this form. This form known as convolution type integral. We have studied this integral in the inverse Laplace transform as I have told earlier. So as we were saying, discussing that the Volterra type convolution integral, we can solve the integral of this form. Can is only solvable through Laplace transform. Let me take an example. As we have studied in Laplace transform that Laplace inverse of and that f of s times g of s through that convolution theorem is equals to integration 0 t f of that u times g of this is should be capital F of u times g of t minus u times du. Now, if inverse Laplace transform of this is this, then through simple manipulation we can say this f of s times g of s will be equal to this Laplace of integration 0 to t f of u and times g of t minus u du. This takes place in such a manner. So this is how we solve the integral. Like this is a base from which derivation or solution of that integral is derived. So let's solve the first problem which I have taken. This is this one. Y of x. This is an integral equation. Y of x equals to x square plus integration 0 to x of this is our f of u. This is g of t minus u of du times. So this is limit is in terms of that. Here it is this. So limit will be in terms of this x. So the very first step will be take Laplace. Take Laplace on both sides. So on taking, so we will get this. Oh, we can write it as wait a minute. Laplace of y of x equals to Laplace of this x square plus Laplace of this whole integration 0 to x this y of t times this sine of x minus t dt. So from here we can say this will be y of s. Converting any kind of domain into a frequency domain This will be, you can treat it as a t to the power n formula. So this will be gamma n plus 1 means gamma 3 upon s to the power n plus 1 will be 3, and then next will be our the main integral. uh, Using this relation we can say this as this will be let consider this will be our f, so it will be y of s. The Laplace of y of t is y of s, converting any kind of integral function any kind of into a time frequency domain function. So in here it is of form of t minus u, so we can write it as sine of t. So sine in Laplace of that sine of t will be 1 upon s square plus 1. The only thing we need to do is now to simplify this expression. Y of s will be equals to, taking this to that side, y of s equals to s square upon s square plus 1. This equals to 2 divided by s cube. Now multiplying this whole thing on that side, y of this s equals to 2 divided by this is s. This will become s square plus 1. This will be like s square s cube. It will be s to the power 5. We can simplify it. We will get to 1 upon s cube plus 1 upon s to the power 5. Now taking inverse Laplace again, we will get to y. Let's take it in a function of x. We will get to 2 times of this Laplace inverse of 1 upon s cube plus Laplace inverse of 1 upon s to the power 5. Now using inverse Laplace transform properties, we can write it as a t square divided by gamma 2 is 1 plus t to the power 4 divided by gamma 5 is 24. Now only thing is clearly simplified. We can write it as a 4, sorry, t square by 12 24 plus t square. So that's our answer. Moving on to our next question, which is this. First step, taking Laplace on both sides, we will get a y of this s. Now Laplace of this will be 1 upon s plus 1 minus 2 times of this. Laplace of this will be y of s times this Laplace of cos of t is s upon s square Laplace of cos will be equal to s square plus 1. Now taking this whole thing over that side, we will get y of s here in bracket we will get s square plus 2s plus 1 divided by this s square plus 1, and that whole equals to 1 upon s plus 1. Now once we will send this whole factor on the right hand side, we will get s square plus 1 upon s plus 1 whole cube. This will be s plus 1 whole square, so we will get s plus 1 whole cube. Now we can clearly see we can simplify the numerator as a s plus 1 whole square minus 2s upon s plus 1 cube. We can write it now as a 1 upon s plus 1 minus 2s upon s plus 1 cube. Let me see if this is correct or not. So now this is a y of s. Now we need to little bit simplify this one more further. We can write once again it as a 1 upon s plus 1 minus 2 times of this s plus 1 minus 1 divided by s plus 1 whole cube. Now we can write it as 1 upon s plus 1 minus 2 divided by s plus 1 whole square plus 2 divided by s plus 1 whole cube. Now only thing left is to take inverse Laplace. Take Laplace inverse on both sides. We will get y of this x equals to this Laplace inverse of 1 upon s plus 1 minus 2 times of this Laplace inverse of 1 divided by s plus 1 whole square plus 2 times of this Laplace inverse of 1 divided by s plus 1 whole cube. Let's see. We have now on taking Laplace inverse we will get, let me solve it here on next page. Now from first shifting theorem, firstly we can simplify all of them in such a way like you can write them as e to the power minus, Let's take this as a function of x. We can say it is a function of x or whatever we want. Even a function of t, e to the x, and this Laplace inverse of 1 upon s. In whole we can take this common, minus 2 times of this Laplace inverse of 1 divided by s square, plus 2 times of this no, Laplace inverse of 1 divided by s cube. Now we can easily take the inverse Laplace of these functions. We will get let's take all the function in e to the power minus x. This we will get 1 minus, here we will get division by gamma 2 is 1, so minus 2t. Here we need to divide by gamma 3, which is 2, so it will be t. eh, Sorry, I have taken it in a function of t. It should be x. hmm. So we will get 2x plus, sorry, it will be x cube. We can write it as a function of t also. So we have got our answer as y of t equals to e to the power minus t t sorry, there should be t here, x square. So t minus 1 whole square, that's our answer. So in our this lecture we have taken two important problems based on integral Laplace application of Laplace transform to solve integral equation. The first one is that, and second one is this. And for our homework question, let me see. I have forgotten to write the homework question. Let me write it also. So for today, your homework will be um, to solve this integral equation. Let me, y of x equals to, let's take a cos h 2x plus integration 0 to x mm, y of t dt. So this is your homework question. I we will solve. The only variation in here is, let me give you a hint. It should be x minus t treated as a, here when we multiplied by 1, and 1 can be treated as x minus t to the power 0. Now I have given you question. I hope you will be able to solve this question. So this was our final lecture. I hope you have understand our lecture. Thank you and have a nice day.